compression system and stable flow as well. I believe that facility was a 1,000 megawatt facility. And then this is a great solution out in New Mexico. Denny, New Mexico. Luna Energy is quite a remote site there in New Mexico. So they opted for on-site generation and also storage at their facility. So they sized the generator so it was a little bit excess generation than what they would typically use on a daily rate. The excess generation rate goes into their storage site here at low pressure. When these come up to pressure, they just valve them off and isolate them. And then the generator ramps its production down and makes just enough gas to keep up with whatever the daily usage of the plant is. When they go into an outage situation, they would shut off the hydrogen generator, do their outage work, whatever it might be. They need to regas the generator. They pull those larger volumes of hydrogen from their stored hydrogen that's been valved off all this time, just sitting, not connected into the plant. Fill their generators back up, start up the hydrogen generator, the daily makeup goes to the plant. The excess generation refills these back to 200 psi or 400 psi. They get valved off again and wait till next year when they go through another outage. It's a very simple, straightforward solution and allows them to be completely independent from hydrogen deliveries. This is one of our newest full project construction jobs. It was actually in Qatar with GE. That facility, it was a 1,200 megawatt facility, and they opted for, because of the location in Qatar, they opted for dual streams of hydrogen generation located here, dual compression systems for high pressure storage for this facility, and also dual high pressure storage volumes as well for storage. Quite elaborate, that facility. I wouldn't recommend that to everyone. They tend to go a little overboard on their capabilities there. It's certainly a great solution for them. So, just to quickly touch on the stable flow system a little more and what we see the benefits of stable flow as for the generation community. And it comes right down to hydrogen gas purity versus efficiency. This is a chart that we've used quite extensively regarding hydrogen purity and its importance for electric generator cavities. Air is the most likely contaminant in an electric generator cavity, and air is 14.4 times more dense than hydrogen. If you picture that, I always like to think about sticking my hand out the window in the car. It's a good, pretty good force on your hand when you stick it out the window. Think of if the gas density outside the window was half. You can kind of get a feel for the amount of the force that would be reduced on your hand. Well, hydrogen is 14 times less than that. So it's not half. It's not half again. It's 14 times less dense than air. Does that make sense? So, the basis for using hydrogen electric generators is, number one, hydrogen is a great conductor, outstanding conductor compared to air, and it's much less dense than air. So by maintaining a high purity in the electric generator cavity, you're minimizing windage losses. And that minimization means you're burning less fuel for the same amount of power output, or you can burn a little bit more fuel for a little bit more power output, depending on how your plant's configured and what the limitations are on the rest of the plant. And that's what stable flow is designed specifically to do, to bring those electric generators that are out there at maybe 95%, 96%, or 93% hydrogen purity, to bring those up to 99. So that you're minimizing the energy in to the spinning of the electric generator and maximizing the electricity out. So this chart just looks at changes in density here. You can see here at 100%, you're good, and as you go down, your density increases significantly. And then this is the chart that we point to quite often, and this comes directly from Power Engineering, from a paper from Siemens, where they did a calculation of looking at windage loss based on hydrogen purity, and then made a calculation about potential savings for a single generator. So they pointed out 1% increase in maintained hydrogen purity, i.e. going from, say, 99 or 98% purity to 99% purity, can translate into 250 kilowatts of reduction in windage loss. So it's 250 kilowatts less energy you have to put in. Or, equivalently, 250 kilowatts extra you could put out for 1% change. So they did a calculation. $320,000 per year savings with a 4-point increase. So they went from 94 to 98, could be 94 to 98, 95 to 99, whatever the 4-point change was, $320,000 for this application. And they assumed 4 cents a kilowatt hour, which is not unreasonable for a price. Maybe a little better now, and 8,000 hours a year of operation. You can kind of plug your own numbers into this, but you can see the savings adds up quickly. And certainly baseload facilities that are coal-fired, the savings adds up significantly. And on top of that, say you're putting out the same amount of power, you could actually reduce your fuel usage, so your coal burn rate could go down.
One of the things you want to point out too, I think I'm correct in saying that a lot of your purity meters are the thermal dispersion type, where you've got a canister molecular sieve in front of the units. That 13X molecular sieve will take out water, CO2, any CO2 that's present, and turbine oil. The meter that's used on this system doesn't take out any of that. It isn't required. So you will actually get a more realistic reading with this system than you typically have in your generator.
Along those lines, in the development of the stable flow, we looked at different purity meters, and we settled on the Yokogawa. I'm not sure if you're familiar with it, the Yokogawa 40GE402 sensor. It's a vibrating element sensor, and what it does is it monitors the sample gases passed by a vibrating cylinder. The vibration frequency of that cylinder changes as the density of the gas passing by the cylinder changes. So they can monitor the frequency they ping the cylinder with and the frequency response, and because of the change in density they can say, oh, it's 100% hydrogen, or nope, it's only 99% hydrogen. And that's what we use, and it's very robust against dust and oil, as Ed pointed out. So from another efficiency side of the equation, looking at CO2. We see a large number of plants around the country that do not operate at 99% hydrogen purity. It's not something that's monitored all the time. It's not something that's proactively followed from what we see, but it's something that can have significant impact on your bottom line over time. So we strongly promote the idea that by improving hydrogen purity for the same amount of energy input, you can produce more electricity, or you can actually reduce your fuel burn. In that case, CO2 comes off your CO2 generation comes out, and in the end, you're at a savings of 1 megawatt equals a ton of CO2. So over a year, it adds up significantly. And with consideration of carbon credits and all this stuff coming along, we believe strongly that this will come into play in the long run and be an added benefit to facilities. And then I have one sheet here from a site that just talks about cost benefits and cost breakdown. And this is something that we typically generate in the applications group within our company. Typically, Ed or our other folks out there would identify a facility, talk with them, and they'd say, we're interested in a stable flow or on-site hydrogen generation solution in general. We would send out a applications form to kind of fill in, looking at your hydrogen usage rate, your generator cavity purities, things of that nature. And if you wanted a full solution, we would generate an application note similar to this. We would look at roughly the layout of a potential system for your facility, and then look at savings under the different aspects of a hydrogen solutions. So under a stable flow solution,